Everyone. So we're going to conclude the module, our discussion of space and time, with a discussion this week of the direction of time and what might account for the so-called arrow of time, the fact that time, unlike space, seems to have a distinctive directedness. So the the sort of starting off point is the observation that although in contemporary physics there's a sense in which time and space are treated analogously. For instance, in a Minkowski space-time diagram, the t-axis is added to the three spatial axes. Well, actually, I mean, you don't include all the three spatial axes. Normally, you suppress one or two of them in your representation. But nevertheless, the t-axis seems to be treated somewhat analogously to the spatial axes. And also, we learn, for instance, there's no absolute simultaneity. So this at least poses a challenge for the notion that there's an absolute present, an absolute temporal present. And so maybe we think, time is like space in that just like there's no such thing as an absolute or privileged spatial present, there doesn't seem to be an absolute or privileged temporal present either. But despite these sort of broad analogies between time and space in contemporary physics, they're not treated in exactly the same way. For instance, even in the special theory of relativity, the t dimension plays a different role in the interval measure than do the x, y, and z dimensions, the spatial dimensions. So interval is increasing in t, but decreasing in x, y, and z. And also there's an important difference between time-like separation and space-like separation. So this has to do with the paths that ordinary objects can take through space-time. They can travel along space-like curves that are such that any 2 points on the curves are stand in time-like separation. In other words, can be traversed without exceeding the speed of light. And on the other hand, curves that are space-like, that can't be traversed by ordinary objects. So whilst there's a certain analogy between t, the time dimension, the x, y, z dimensions, they're not treated identically, even in STR and Minkowski spacetime. And also we think, I think, on a sort of maybe more intuitive level, and maybe in the other sciences too, that there's a difference between time and space. Certainly, it seems that time has a direction to us, and we might also say it seems to pass or flow, whereas we don't tend to think of space as flowing or passing in the same sense. And although, obviously you can talk about directions in space, it's natural to think of them all as relational. So I can talk about left and right, but that's relative to my orientation. I can talk about up and down, again, relative to my orientation. Or, sometimes we might use other objects like the Earth when we talk about west and east and so on. So none of these, there doesn't seem to be sort of any kind of universal or objective facts about up and down, left and right, west and east. They're all relativized to particular objects in space. Whereas we might be more persuaded that there's an objective arrow of time. So there are a couple of questions. So what, if anything, then accounts for the passage of time or the flow of time? Or is it just an illusion? So people like McTaggart argue that our experience of the passage of time is illusory. Then there's another question: what, if anything, accounts for the directedness or the asymmetry of time, or as it's sometimes known, time's arrow? Now, it's important to bear in mind that these really are different questions. So they might be related, but they're certainly not the same. So time might have an asymmetry or even asymmetries, even if it doesn't have a passage or a flow. So there are lots of entities that have asymmetries, but that don't have any such thing as a flow or a passage. So, if you think about things like, the counterexamples of incongruent counterparts like hands or the letter L, they have asymmetries, but they don't flow. There's no flow of hands, but there is an asymmetry of hands. So likewise, when it comes to time, we should separate these questions. Does it have an asymmetry? Does it have a flow? Having said that they're different questions, it's possible that they're related, although they're not necessarily related. So, for instance, if time does have a flow, an objective passage, then this might be, or at least account for, the asymmetry of time. So, for instance, if it has a flow, then presumably the flow is away from the past and towards the future. So the flow is in one direction along the t-axis, if you like, along the temporal dimension, and that would give you a directedness, an arrow of time. But you could still believe in an arrow of time even if you didn't believe in the flow of time, and that's pretty important for the B theorist, as might have occurred to you. So according to the B theorist, there is no flow of time, and so they typically share McTaggart's qualms about the notion that time passes or time flows, and yet they still want to preserve an asymmetry of time because the B relations of earlier than and later than are asymmetric, right? So they need that asymmetry even though they deny the flow. So the asymmetry, it looks like, has to come from somewhere else. So focus on the A theorist for now. So the A theorist might just think, okay, well, we just can account for the arrow of time, the directedness, in terms of the flow. So the question of what accounts for the arrow might be less pressing for them. So the A theorist, of course, believes that there are absolute facts about what times are past, present, and future, that these absolute facts change, potentially giving us this flow. I suppose the story might go differently depending upon what form of A theorist you are. So presentists are normally regarded as A theorists. They might attempt to, obviously they account for the flow of time in terms of existence. So only the present exists, but what used to exist is different from what does exist, and what's different from what will exist. This gives us a flow. And maybe it gives us an arrow, right? So the distinction between what did exist and what will exist maybe provides an arrow of time. Growing universe theory, again, normally considered a form of A theory, might try to account for the arrow of time in terms of the distinction between what will be, or what is on the growing edge of the universe, what will be on the growing edge of the universe, and what exists but is not on the growing edge of the universe. In other words, what's past. So again, this gives us a natural interpretation of the arrow, which again is sort of parasitic on the growing universe theorists' account of flow. The moving spotlight theorist, remember, the moving spotlight theory is the combination of eternalism with the A theory. So according to them, there is all, past, present, and future all exist, but a certain moment in time has this property of presentness, and which moment has the property of presentness changes. And so they could account for the arrow of time in terms of the direction of change, right? So there's a moment that does have the property of presentness. There are moments, presumably towards one end of the t-axis, that did have the property of presentness, and there are other moments towards the other end of the t-axis that will have the property of being present. So again, this seems to be a way of understanding an arrow of time in terms of the flow. So I guess what all these theories have in common, in a sense, is that they all think of time as passing or flowing, but there's and this gives us a direction, because there's a direction in which time passes or flows. It flows from the past to the future. But obviously the B theorist can't avail herself of the notion of flow or passage in defining the arrow of time. So the B theorist might share McTaggart's qualms about the A properties, about the A series. They might think that the notion is incoherent, or they might object to the A theory for other reasons. So, for instance, remember the worry about the rate of passage. So they might think that there's no sensible answer to what rate time flows at or passes at, and so they might think that the notion of a passage or flow is of dubious coherence because of that. They might, on the other hand, worry about the A theory on grounds of question marks over its compatibility with special relativity and the relativizing of the present. So for one reason or another, the B theorist is going to be suspicious of, and indeed reject the A series, and with it the objective passage or flow of time. Nevertheless, the B theorist, as I've already mentioned, needs to endorse an asymmetry or an arrow of time, because they need to understand the difference between earlier than and later than. So these B relations are asymmetric, so it seems we need an asymmetry in time. So a lot of what we'll focus on this week is what the prospects are like for a B theorist to make sense of an arrow of time. So a lot of discussion, there's been a lot of discussion about whether we can provide some basis in physics for understanding the arrow of time. And if we can, then that would be a good thing for the B theorists, because, well, assuming that basis in physics didn't have anything to do with flow, then the B theorists could avail themselves of that physical asymmetry to explain the difference between earlier than and later than. Okay, so that's largely what we'll be looking at this week. Now, it connects in quite an important way with last week's topic, because the question of whether time is fundamentally asymmetric is perhaps informed by the question of which of the models of space-time that we looked at last week, if any, it holds. So some of those models, if they held, would make it difficult to sustain a fundamental or universal asymmetry of time. So, for instance, we considered a model on which everything lies far in its own future. So the whole of space-time, if you like, curves round on itself. So everything lies in its own absolute future, just as, every object, I guess, on the surface of the Earth lies far to the west of itself. Now, if space-time were like that, and we have no reason to think that our space-time is like that, although such spacetimes do seem to be permitted by the field equations of general relativity. If spacetime were like that, then it would be rather difficult to sustain the notion that there's a fundamental asymmetry, or at least certainly a universal asymmetry between the past and future directions of time, because everything's far in its absolute future and also far in its absolute past. So maybe that would pose a problem, but we might still think that ours isn't a world like that, and so maybe ours is a world in which there is a universal and fundamental asymmetry of time. Okay, so let's assume that we think that there is an asymmetry of time. We're prepared to get on board with that, at least in our universe. We don't have to necessarily commit to there being the same sort of asymmetry in all possible worlds, but in ours, it seems that there is. Now, I mean, we talk about the asymmetry of time, but various philosophers, metaphysicians, philosophers of physics, physicists have noted that actually there are a number of asymmetries associated with the direction of time. And there's a partial list on the handout. So there appears to be an asymmetry of causation and explanation. So things that are earlier in time tend to causally explain things that are later in time, and not vice versa. So, setting aside, these unfamiliar possibilities of time travel, then it seems that generally we have the causal explanation of later events by earlier events and not vice versa. A second asymmetry is an asymmetry of knowledge, or perhaps more broadly an asymmetry of records. So we seem to know more about the past than the future. And in general, there seem to be more records of the past than records of the future. So our memories might be among the records of the past that there are. So as I say on the handout, so we've got video and audio recordings of the past, written records, tree rings, fossils, memories. So these are all sorts of records that we have of the past, but we don't seem to have anything like such extensive records, if indeed we have any records of the future. And presumably this asymmetry of records accounts for the asymmetry of knowledge, the fact that we know more about the past than the future. Now, we'll come back to this, but you might think, well, maybe this asymmetry of records is closely related to the asymmetry of causation, because, a record is an effect of the thing that caused that effect. And so, because the past can cause things in the present, that explains why we have records of the past, whereas the future, at least ordinarily, we don't think that it causes things in the present, and so we don't have records of the future. Another asymmetry, which maybe takes a little bit more unpacking, is something that Hans Reichenbach, so I've given the citation at the end of the handout, refers to as a fork asymmetry, which again seems to be rather closely related to the asymmetry of causation. So this fork asymmetry that Reichenbach points to is the fact that we often find that later correlations can be explained in terms of earlier events, but not in terms of later events. So in other words, we find that correlations can be given explanations in terms of common causes, but not in terms of common effects. So that's rather abstract. Consider an example. Reichenbach gives us a very similar example. Suppose that we find that lots of people get ill with the same symptoms. Then how do we explain this? Well, we look for some past explanation, some past cause, if you like, of the correlation. So, for instance, were these people all in contact at some point? Did they all eat the same thing? And if we found that, at some point they were all, attended a party together, or maybe they all ate the same batch of some ready meal that was sold by a leading supermarket, then we might be satisfied that we've identified an explanation for the correlation between these people's symptoms. But we wouldn't, by contrast, expect an explanation of these correlations in terms of some future event, right? So we wouldn't seek or expect to be able to explain the fact that all of these people fell ill with similar symptoms in terms of the fact that they all will meet at some time in the future or will eat the same thing at some time in the future. So this is the fork asymmetry that Reichenbach talks about. There seems to be an asymmetry of action. So we're able to influence the future, but we're not able to influence the past. In some sense, the past seems to be settled and the future open. That's something we've talked about before. Again, you might think this is closely related to causal asymmetry. So we're able to act now to causally influence the future because of the direction of causation, but we can't causally influence the past. Okay. Finally, another interesting one, which will take a bit more elaboration and which we'll return to later, is the asymmetry of entropy. So this is a little bit more technical, physics-based. So entropy is a measure of disorder, and the asymmetry of entropy is captured by a well-known principle of physics known as the second law of thermodynamics, which states that the total entropy of the universe increases over time. Disorder increases over time. That holds for the universe, but also for systems within the universe. We'll come back to exactly what that means later. Now, okay, so granted we've got at least 5 asymmetries. It's natural to ask, well, what's the relation between these asymmetries? And also whether we might seek a reduction of the temporal asymmetry, that is the direction of time, to one or more of these, right? So we've got an asymmetry of time, we've got a bunch of corresponding asymmetries. Can some of these be reduced to others, right? So that's a natural metaphysician's question. So, we seek parsimony in our metaphysics. So it would be nice for parsimony reasons if we could explain some in terms of the others. There might be something more to it than pure parsimony. So it might be that, look, it seems a bit peculiar that we should have all of these asymmetries that all line up in the same direction. So we want an explanation for that. And it would be nice if we could explain maybe all of these asymmetries in terms of one of them, or all the rest in terms of one of them. Now, a promising bet might seem to be the asymmetry of causation, because we've already seen that the asymmetry of causation seems to be at the root of many of the other asymmetries mentioned above. So the fact that the asymmetry of records, for instance, we noted, seems to be related to the asymmetry of causation. So something is a record of an event only if the event caused it. So the example on the handout is, for instance, for something to be a film of the moon landings, it must be that the moon landings caused the record, right? Caused the images that we have. Otherwise, this wouldn't be a genuine film of it. It wouldn't be a genuine record of the moon landings. The asymmetry of knowledge, again, we noted, seems to have something to do with the asymmetry of causation. So this is partly accounted for in terms of the asymmetry of records, but maybe more generally by the fact that knowledge arguably involves having beliefs that are caused in the right way. So, for instance, we have knowledge of the past because past states cause our present beliefs that furnishes us with knowledge. But whatever our beliefs are of the future, well, normally those can't be caused by events occurring in the future. So maybe this accounts for why we don't have genuine knowledge of the future. The fork asymmetry we noted is an element of the causal asymmetry. So present correlations tend to be explained by past events, but not by future events. And action asymmetry, again, seems to relate to causal asymmetry. So we can cause things to happen in the future. Present actions can cause things to happen in the future, but not in the past. So it might seem somewhat promising to try and reduce some of these asymmetries to the causal asymmetry. It's much less clear that the asymmetry of entropy could be explained in terms of the causal asymmetry. And actually, some people have suggested that it's the other way around. I mean, there's nothing really conclusive here. So, there's definitely no consensus that the direction of causation could be explained in terms of the direction of entropy increase. But some people have at least speculated that that's so. And, maybe that would be a good thing because causation in itself is quite a mysterious phenomenon. So there's a lot of philosophical ink being spilled over the nature of causation itself. What exactly is causation? And not much consensus on that. So maybe if you could somehow reduce at least an aspect of causation, its directionality, to entropy increase, which is a reasonably well-defined physical phenomenon, then maybe that would be a good thing. And then maybe in turn, if you could explain causal asymmetry in terms of entropy asymmetry, and you could explain the other asymmetries in terms of causal asymmetries, then everything would have at its root this entropy and asymmetry. But that's an optimistic claim. So certainly it's not been defended well enough to gain anything like universal acceptance. Okay. So let's just set aside entropy asymmetry for the moment. We'll return to it. So let's start with the idea that maybe we could account for the asymmetry of time in terms of causal asymmetry, whether or not that could be further reduced to entropy asymmetry. So the idea would be as follows. So if we consider the if you like the t dimension, the time dimension, or what McTaggart calls the C series, so this fourth dimension in addition to the spatial dimensions. Well, a dimension consists of an ordered series of points. So we can order points in time or points on a t-axis from one end to the other, just as we can order points in space, points on, say, the x-axis from one end to the other. We don't yet have a privileged directionality, so just because we've got an ordering, we haven't yet said whether one end of the order is the earlier times or whether it's the other end of the order that's the earlier times. So we can denote times tn plus 1, tn plus 2. I guess the ellipses indicate the fact that we're not committing to a first moment in time or a last moment in time. We might do, we might not. Then we want to know basically, is it the t's with lower subscripts? So maybe the t's towards the left-hand end of the ordering as it's written on the paper, or is it the t's with the higher subscripts, those towards the right-hand end as it's written on the paper? Which of these are the earlier times, and which are the later times? So if we sought a reduction of the direction of time to the direction of causation, presumably we would say that, well, it's the t's with lower subscripts that are the earlier times if events that occur at times denoted by t's with lower subscripts tend to cause events at times denoted by t's with higher subscripts. So if it, in other words, it was the events that were occurring at times denoted at the left-hand end of the ordering, tend to cause those occurring at times denoted on the right-hand end of the ordering, then we'd say it's the ones written towards the left that are the earlier, and those written towards the right that are later than. Or it could be the other way around. It could be that the events occurring at times with higher subscripts tend to cause events occurring at times denoted with the lower subscripts, and in that case it would be the ones denoted with higher subscripts that would be earlier than those with lower subscripts. So that would be the obvious way of trying to account or define a direction of time in terms of a direction of causation. Okay, now, so are there problems with attempting to reduce the direction of time to the direction of causation? Well, unfortunately, yes. So there are a couple of, maybe three. So I guess one that I haven't mentioned on the handout is that we might find, it maybe relates to the second one that I mentioned on the handout, we might find the direction of causation itself mysterious. So we might be reducing something mysterious to something that's also mysterious. So maybe you might have qualms about that. Obviously, if causation could be reduced, or the direction of causation could be reduced to the direction of entropy increase, then given that entropy increase is a reasonably well-defined physical phenomenon, maybe that could eliminate the mystery. But still, we've got issues. So one objection would be that if we reduce the direction of time to the direction of causation, then it becomes quite difficult to allow for the possibility of backwards in time causation. This would, the worry is that we would potentially be ruling out backwards in time causation by definition, because we just define the direction of time so that causes occur earlier than their effects, or in other words, later times are the times when effects occur and earlier times when causes occur. Now, although backwards in time causation is certainly controversial, many people would be reluctant to rule it out, certainly sort of definitionally. So if time travel is admitted as a possibility, then it seems that backwards in time causation would have to exist. So, I mean, we looked at, for instance, the example where I travel backwards in time through a wormhole and hand my younger self a book of instructions for finding the wormhole, then that would seem to be a case of backwards in time causation. My possession of the book of instructions at the later time causes my possession of the book of instructions at the earlier time. certainly would generate a bit of a difficulty in making room for the possibility of time travel and backwards in time causation if we simply defined the direction of time in terms of the direction of causation. I mean, it's not altogether impossible. So, you might try something clever like saying, well, the direction of time is the direction in which the majority of causation occurs. And that would allow for exceptions. Suppose there were localized wormholes that allowed causation to go in a direction contrary to the usual direction, then that, I suppose, wouldn't prevent us from defining the direction of time as the direction in which the majority of causation occurs. Or indeed, you might say, well, the causation is just differently directed in these wormholes. That accounts for the fact that they are peculiar in terms of the direction of time. So maybe we have local exceptions to the direction of time and the direction of causation when we travel back through a wormhole. So there's certainly possibilities there. Another issue, though, is that if we sought to reduce the direction of time to the direction of causation, we then would presumably rule out reducing the direction of causation to the direction of time, because that would be going in a circle. But interestingly, many philosophical accounts of causation do seek to reduce the direction of causation to the direction of time. So, for instance, any of you are familiar with the debate probably know how this goes. So, for instance, Hume, maybe one of the most famous, attempts to define causation, a so-called regularity theory of causation. So basically, cause and effect, causes and effects are correlated, and the way we distinguish cause from effect is in terms of time. The cause is the one that occurs earlier in time of the two correlated events. So Hume says that a cause specifically is an event that occurs prior to, contiguous with, that is next to in space and time, and is constantly conjoined with the effect. So crucially, the way that cause and effect are distinguished is by time, so the cause is the one that occurs earlier. And it's not just Hume's account, but many accounts of causation seek to reduce the direction of causation to the direction of time. And the problem is, obviously, that would be circular if we also sought to reduce the direction of time to the direction of causation. Okay. So maybe there's another approach, right, that appeals to something like the asymmetry of entropy. Maybe it can avoid these problems. Maybe it can avoid some of these problems. And certainly it's been a sort of reasonably popular recent approach. Several philosophers of physics, so originally I think Hans Reichenbach, more recently David Albert and Barry Lower, have argued that the asymmetry of entropy captured by the second law of thermodynamics is fundamental to the direction of time. So this is sort of, it could be quite nice because we'd then be given a kind of a physics-based explanation of the direction of time. The account in terms of causation is not quite so clearly physics-based because physics doesn't give us a clear definition of what causation is. That's more of a metaphysical project, whereas physics provides us with a reasonably clear account of what entropy is. So, what does the second law of thermodynamics say? Well, the second law of thermodynamics says that entropy, or in other words, disorder, increases over time in systems that are appropriately isolated. So the universe as a whole presumably is an isolated system. and so within it, it's assumed that entropy increases over time. So the Big Bang, or at least shortly after the Big Bang, um, mass and energy were highly concentrated. The state of the universe was very dense, very hot, and the idea is that slowly over time, well, actually quite rapidly over time, the universe has been expanding and cooling, and so the hot and dense state is considered an ordered state, one of low entropy, whereas the spread out and cool state is considered a state of high entropy or higher entropy, higher disorder. And so this would be an instance of the second law of thermodynamics. So one hypothesis about the fate of the universe, the heat death hypothesis, is that eventually the universe will be a state in which matter is spread out very widely and temperature is more or less uniform. So a very, very high entropy state as opposed to the low entropy state or the ordered state that the universe began in. Now, it's not just on the ground scale of the universe that entropy increases, but there are also more localized instances. So, for instance, processes of diffusion and osmosis, whereby molecules spread out over time, they're entropy increasing processes. So processes of ice cubes melting in hot water, coffee cooling after being removed from a heat source, processes of decay, processes of objects slowing due to friction, because these involve the object's energy being dispersed into its environment. So, in order to sort of see the close association between the direction of time and the direction of entropy increase, you can consider a thought experiment. Suppose that a friend of yours takes a video and they're going to show the video to you, and they're not going to tell you whether they're playing it forwards or backwards. We'll suppose that the playback in reverse is exactly the same speed as the forwards playback, and that there's no screen distortion or image distortion with playback in reverse. Now, there's a good chance you're going to be able to tell whether it's being played forwards or backwards. I mean, obviously, if your friend just films a brick wall for 2 hours, then you might not be able to tell. But assuming they film something more interesting, there's a good chance. And arguably, the reason you'll be able to tell is because entropy increasing processes are highly pervasive and they look very weird in reverse. So, for instance, it would look weird to see an ice cube spontaneously forming out of hot water, to see a milk unmixing in coffee, to see a stationary football spontaneously start to roll and gather speed until it hits a footballer's foot, which would then be propelled backwards. So this would be the reverse of an object slowing due to friction, which is an entropy increasing process. When it comes to, another sort of way you'd be able to tell is through the actions of people. So people walking and talking backwards. I suppose it's a bit less clear cut exactly how this relates to entropy increase. But I mean, we can say that the biochemical processes that underlie the walking and talking, maybe even the conscious processes, are entropy increasing biochemical processes. So, most of the processes that are required to sustain you and for you to act and maybe for you to think, right? So processes like the passage of neurotransmitters across synapses, these are entropy increasing processes? So, I mean, there's a sort of good question. So, does that mean that basically um, uh, your actions? I mean, so your actions are, or they seem to be explained by entropy increasing processes. So again, maybe this sort of symptom of whether the video is being played forwards or backwards is itself either an entropy increasing process or at least explained in terms of entropy increasing processes. So there seems to be, I suppose, a very tight link between our experience of time as having an asymmetry, or our thinking of time as having an asymmetry, and these processes, these asymmetric processes that all seem to be entropy increasing processes. So there might be a suggestion, and indeed there is a suggestion among some philosophers of physics, that the direction of time can just be reduced to the direction of increasing entropy. The direction of time just is the temporal direction in which entropy goes from low to high. So if you think about the way the second law of thermodynamics is stated, well, maybe this looks circular. So the second law of thermodynamics says that entropy increases over time. So it sounds like we take for granted the direction of time in stating it. But actually the sort of circularity then of defining time in terms of entropy increase is illusory, because we don't actually need to presuppose the notion of time. We could just take our ordered set of times, right? So our dimension, our t dimension or our t axis, and if we were to try to reduce the direction of cut time to the direction of entropy increase, then we'd say that well, the t's with higher or the times denoted by t's with higher subscripts in our order count as later than those with lower subscripts, if and only if entropy is higher towards the end of the dimension denoted by t's with higher subscripts than towards the end of the dimension denoted by t's with lower subscripts. Or conversely, if times denoted by t's with lower subscripts were times of higher entropy than those denoted with t's with higher subscripts, then we'd say the times denoted by t's with lower subscripts were the later times. So we can give that analysis without circularity. Okay. All right. So maybe that's right. So I guess we have the sort of question of whether we can. So if it's plausible that the direction of time could be reduced to the direction of entropy increase, and this is by no means settled, although people have claimed this, we might wonder to what extent the asymmetry of entropy can explain the other asymmetries that we associate with time. And there's a sort of detailed debate on this by people like Reichenbach and Albert and Lower. So they've tried to make a case that the asymmetry of entropy can explain these other asymmetries that we associate with time, like the asymmetry of knowledge, the asymmetry of records, maybe the asymmetry of influence, and so on. Now, again, it's the state of the literature at the moment is rather speculative, so it's not been worked out in very much detail, has to be said, but they've provided hints about how these explanations might go. So, for instance, the asymmetry of entropy increase might have something to do with the records and knowledge asymmetries, if somehow it's easier to know about and for records to be produced of orderly states, which tend to lie in the past, than disorderly states, which tend to lie in the future. And indeed, there's been suggestion that the creation and observation of records itself depends upon entropy increasing processes. For instance, the radiation of energy from the sun is required for photographs to be produced or films to be produced and to be observed. So maybe the creation and observation of records depends upon entropy increasing processes, which might explain why we have and observe records of the past but not of the future. What about the causal and explanatory asymmetry? Well, it's been suggested that maybe we conceptualize the world in such a way that we see simpler or more orderly states as causally explaining less orderly ones. And when it comes to the asymmetry of influence, maybe we find it easier to intervene on more ordered states than less ordered states. So, for instance, maybe it's easier to intervene on an ice cube by putting it in coffee than it is once the ice cube has melted to intervene on the water molecules that used to constitute the ice cube to maybe impart the momentum on them that would lead to them reforming into an ice cube. So maybe this has something to do with the asymmetry of intervention too. But, I mean, there's a lot of sort of details required here to make this all very plausible. Some of the details are provided by Reichenbach and Albert, so if you're interested in those details, I'd encourage you to follow up those references. But I think it's fair to say that it's not, been anything like conclusively established that this all works out. Now, suppose that something in the ballpark's right. So suppose that we can reduce the direction of time to the direction of entropy increase. Well, one interesting feature of the second law of thermodynamics is that actually it doesn't simply say that entropy increases over time. Rather, it implies that entropy increases over time until equilibrium is reached. Equilibrium being a state of maximum entropy. For instance, where mass and energy are uniformly distributed. And once a system is in equilibrium, it predicts that it will remain more or less at equilibrium. So if the Big Bang is a low entropy state and the heat death is, if it's anything like an equilibrium state, then the second law predicts that the equilibrium state, the heat death state will be sustained. It's the universe is at least very unlikely to move out of equilibrium once it's been reached. So, what would a heat death state be like? Would it be a state? Would it be a state on this hypothesis in which there was no time? There was at least no temporal asymmetry once you're in that state. That's an interesting question. Another interesting fact is that the second law of thermodynamics holds only probabilistically. So it's merely overwhelmingly likely that an ice cube placed in a glass of hot water will melt rather than becoming bigger. So actually, statistical mechanics implies that there's a chance, albeit a very small chance, that if you place an ice cube in hot water, then it won't melt, but rather it will become larger and colder while the surrounding water becomes hotter. The chance is so astronomically small that it's astronomically unlikely that anyone would ever observe this, that this would ever happen within human experience. But nevertheless, statistical mechanics implies that there's a probability of it happening, just an exceedingly small one. Now, what's interesting is that, if given enough time, given that entropy increasing processes are occurring constantly, given enough time, we'd expect that eventually you'd get the case of an entropy decreasing process. So, because the second law of thermodynamics only holds probabilistically, so given enough time, the small probability of entropy decrease would be realized. So, if there are enough instances of meltings in the universe, if the universe is big enough, maybe temporally big enough as well as spatially big enough, then eventually, sooner or later, I guess law of large numbers, you're going to get an ice cube growing, or a bit of ice growing and getting colder in hot water rather than vice versa. Now, actually, what's interesting is that the universe itself isn't supposed to be an entropy increasing system. So, given eons and eons of time, it seems that it would then become likely that you'd get at least some periods of time over which the entropy of the universe as a whole decreased rather than the usual increase. So the question is, or an interesting question is, if the universe as a whole wasn't always increasing in entropy, either because it's in equilibrium, so the heat death sort of state, or because entropy actually decreases occasionally for a while, just because there's a small probability of decrease at any given time. And so if the universe goes on long enough, then the probability that entropy decreases at some time or other becomes a lot higher. So does that mean then, according to those who think that the direction of time can be reduced to the direction of entropy increase, that there are parts of the t dimension that don't have directionality, or parts that even have the opposite directionality to others? So this is sort of illustrated in figure 1. We've got our t dimension. So maybe on the left-hand end, you've got the Big Bang. So entropy increases until the end of the first arrow. So you have, an arrow of time corresponding to the arrow of entropy increase. But then suppose, just as a matter of chance, because we suppose that eons and eons have elapsed, we get a period, maybe it would be a shorter period, I haven't illustrated that on the diagram, of entropy decrease. Well, would that mean that time, the arrow of time was reversed for that portion of the t-axis, because now entropy is decreasing rather than increasing, and we understood the direction of time in terms of the direction of entropy increase. So initially it's increasing as t becomes greater, but now it's decreasing as t becomes greater, or in other words, increasing as t becomes lower. So do we regard this as a part of the t-axis along which time is the direction of time is reversed? Likewise, we might get, if you like, equilibrium states where entropy is maximal. It's neither increasing nor decreasing. Do we say during those phases that there's simply no directionality of time at that point on the t-axis? So maybe the heat death state. So these are sort of interesting questions for the those who advocate a reduction of time's direction to the direction of entropy increase to answer. Now, it's interesting in this context that various cosmological models seem to have different implications for the entropy profile of the universe. So, according to one model, the universe begins in a Big Bang state, progresses to a heat death state, so a state of thermodynamic equilibrium, or at least more or less equilibrium, and so maybe a timeless universe. But and this again is sort of leads us into an issue that's not very clearly resolved. So, which has to do with the interaction between entropy and gravity. So, some models of the universe on which there is more than a certain threshold amount of mass energy lead not to a heat death, but rather to a big crunch. So the universe collapses back in on itself, and then again a singularity occurs, the big crunch, which is kind of the opposite of the Big Bang. Now, so things are a little bit complex, as I say, because the sort of how gravity affects entropy is kind of an open question in physics. But one interpretation of what's going on here is when the universe starts collapsing in on itself again, that's an entropy decreasing phase. So you could see this as a view in which there are singularities at both temporal ends of the universe, so the Big Bang and the Big Crunch, and the universe is symmetric around some midpoint where its entropy is highest. So, if you like, we have the Big Bang, entropy increases, the universe expands and cools, but then you get to a tipping point where the universe starts collapsing in on itself again, so it contracts and heats up. And so there you'd have perhaps a universe in which entropy is low at both ends of the temporal dimension, and it's at its highest at some midpoint. So it seems that in this case, after the temporal midpoint of the universe, it would be like watching a video in reverse. And arguably, at least it seems, that any inhabitants of the universe after this temporal midpoint would regard what we call the Big Crunch as instead the Big Bang, and what we call the Big Bang as the Big Crunch. So arguably, these people would experience their part of the universe as involving things running forwards, with energy radiating out of stars, ice melting in hot water, all the neurotransmitters diffusing across synapses in the usual way and giving rise to the usual processes of conscious thought and action. And presumably they'd regard our end of the universe as like the film running backwards, so energy being absorbed by stars, ice forming out of tepid water, and so on. Now, this is a very interesting scenario, and it would be a bit odd to maintain that the inhabitants of one region are right about which way the arrow of time points, and the other inhabitants of the other region are wrong. So again, we get back to this sort of suggestion that perhaps the arrow of time might not, if on this entropy hypothesis, might not point in the same direction throughout the whole of the time dimension. And I mean, arguably also, this sort of scenario provides some sort of support for the entropy hypothesis, because it shows how deeply the arrow of time, our intuitive notion of the arrow of time and the arrow of entropy increase are connected. But yeah, I mean, as I say, the whole topic is more characterized by speculation and debate and hypothesis than consensus, anything like consensus. it doesn't seem that the sort of detailed enough demonstrations or arguments have yet been put forward to have people sort of crystallize around a sort of consensus position on whether we can or not understand the direction of time in terms of the direction of entropy increase. But it's certainly a sort of fascinating hypothesis, and I suppose a sort of exciting area of philosophy of physics, precisely because things do seem to be so open. Okay, but that's it for this topic. As I say, if you're interested in reading more about it, there's more on the further reading list for this week. And that concludes the entire module. So I hope that you enjoyed it, that you got something out of it, and I the obviously you've got the sort of formative essay to write. And the deadline for that will be the 26th of April, 4 p.m. So the full details are provided on the course Moodle page. Now, obviously, some of you will be having self-certified extensions or extensions via the extenuating circumstances mechanism, but for anyone who doesn't, then the deadline is the 26th of April. And just a reminder that the list of essay questions is available on the course Moodle page, that you can write on the same topic, the very same question, for both the formative and the summative essay. So if you want your summative essay just to be an expanded version of your formative essay, hopefully taking into account the feedback that you received on the formative essay, then that's absolutely fine. And if you have any questions about the summative essay, then please do let me know. Just send me an email. Otherwise, thanks for attending, and I'll see my seminar group on Tuesday. But to the rest of you, if I don't hear from you beforehand, have a great break. And yeah, thank you very much. Goodbye.